In today's tutorial, we're going to create a real Plexus by using a new set of nodes that have been released in Blender version 4.0. That's the repeat zone set of nodes, and it's one of the most anticipated nodes that I've been waiting for its release. We've created other Plexus style animations before, and we've used many other techniques to do it. However, this time, because we have the repeat zone nodes, we should be able to do this in a more intuitive manner. So if you want to check out how to do it without using the repeat zones, you can check out this tutorial over here. But until then, let's figure out how to create a Plexus style animation using repeat zones in Blender version 4.0. In our default scene, we'll go ahead and bring our cursor to the junction of these two windows. We'll click and drag to create a new window, and we'll change this from the 3D viewport to the geometry node editor. Then we'll press this plus button to create a new geometry node tree, and we'll go ahead and delete the group input. Now the main idea is to have a bunch of points distributed either on a face or within a volume, and then have lines drawn between those particular points. So let's go ahead and press Shift A and search for a grid plane and just plug that into the group output. Now you could do this with a cube, which you could then change to a volume, and then you could distribute points within volume as shown in the previous videos. However, in today's video, I'll just go ahead and use a 2D plane itself. Let's go ahead and change the size to something like 5 meters so that it's a bit larger, and then let's distribute points within this face by searching for a distribute points on faces node. Now I'm going to reduce this density from 10 all the way down to something like 2, just so that it's much faster on my laptop, because I'm also recording and I don't have the greatest graphics card. Now let's go ahead and give these points some random motion, or at least some random positions, by searching for a set position node, and we're going to control it using the offset, and we're going to control the offset using some form of noise. So let's search for a noise texture, and you can plug this in directly over here, but everything shifts to the top right. So to move it back, we're going to search for a vector math node, and we're going to go ahead and subtract a value of 0.5 on all of the axes to bring it back down to the original position. Now, if you want to create the motion as a looping motion, you could use some custom nodes like this looping noise node right over here. And in case you want to learn how to create a node like this, you can check out this video over here where we go step by step on how to do this for the shader editor. The same steps would apply for the geometry node editor as well. However, I will create a dedicated geometry node version very soon, so stay tuned for that. However, for today's purposes, I'm going to go ahead and actually increase the amount of offset by searching for another vector math node and changing this from add to multiply, and multiplying a value of maybe something like 10 on all of the different axes. So now you can see we get quite a bit of movement. However, to actually get this to move, we're going to change this from 3D to 4D, and we'll play around with this W value. So you can see how this W is causing all of these particles to move. Let's go ahead and search for a scene time node followed by a math node so that we can actually control the speed of the animation, and we'll take the seconds, plug it in, and we'll divide it by maybe a value like 10 and plug that value into the W. Now when you play the animation, you can see it's moving way too fast, and that's happening because we did not divide it, instead we added. So let's change this from add to divide, and now you should get a much slower animation, and this looks great. But let's choose the correct frame rate as well. So let's go to our output properties, change the frame rate to maybe 60 frames per second, and then just play the animation, and you can see what the speed currently looks like. If at all you don't get 60 frames per second over here, you can change the playback from play every frame to frame dropping so that you get a realistic idea of how fast these particles are going to be moving. I still think this is moving a bit too fast, so I'm going to divide it by a value of 20 so that they move much slower, and I think that looks great. Let's make the end frame something like 600 so that it becomes a 10-second long animation. Now the next thing that we have to do is actually create lines between this, which is the main bulk of the animation. For that, we're going to use repeat zones. So let's press Shift A and search for a repeat zone section. Let's go ahead and plug the geometry into the input geometry and the output right over there. So let's go through a bit of theory of how this repeat zone works, and then we'll go into theory of how the actual animation is going to work, and then we're going to create the repeat zone section. So essentially, the repeat zone is similar to the simulation nodes, where whatever input geometry comes in over here gets manipulated, and then the manipulated geometry is brought back right over here, and then it's manipulated once again. Now this is going to happen as many times as you determine in this socket over here. So if I say 5 times, whatever we have over here is going to repeat 5 times. So if I was to search for a set position and I was just to move it on the x-axis by 0.1 units, or let's actually make it 1 so that you can actually see the motion, it's going to move by 1 unit and then it's going to come all the way back here and repeat once again. So it's going to move by another 1 unit, then another 1 unit, and it's going to do that 5 times. So it's moved 5 units in total. So that's exactly what the repeat zone does. Now let's figure out how we're going to use this to our advantage to create these particular lines. Let's see what the problem at hand is. If we have, let's say, 5 unique points, so 1, 2, 3, 4, 5, that have indices 0, 1, 2, 3, and 4. We need to connect lines between all of them, and later on we'll delete the lines that are too long. So first, to create lines between all of them, we're going to have to iterate through each and every single point. So that's very important. The first number of times that we need to iterate is going to be through each and every single point. So let's see, at point 0, how many times do we have to draw lines? We have to go from 0 to 1, then from 0 to 2, then from 0 to 3, then from 0 to 4. So that is going to be the number of lines that have to be drawn from 0. Then we're going to have to switch over to point number 1. Now from point number 1, we have to go ahead and draw lines to every other point, but there's already one line drawn to point number 0, so we don't need to draw that line again. Instead, we're going to start from 1 and directly go to point number 2, then point number 3, then point number 4. Now that we're done with 1, we can go all the way to point number 2. For point number 2, 0 and 1 is already done, so we only have to go to point number 3 and then point number 4. Then at point number 3, we have to go only to point number 4. After that, we can notice that point number 4 already has all the lines drawn, so we don't need to do anything for point number 4. So overall, the number of iterations is going to have to be equal to the number of points minus 1. So that is the first main loop. However, when we were at each of these points, we had to go again and repeat an action some number of times. So within this repeat zone, we're going to have to repeat again. So we're going to have something called a nested loop. So if you understand computer code, you'd know how we have nested loops where we have a for loop and we'd have some variable such as I going from some value to maybe some other value. So let's say we have to make sure that I is less than 10, and then we could just increment the I, and whatever we write code within this section would repeat. And to create a nested loop within this code, you'd have another for loop where you'd have a different variable, maybe something like J, and that would also happen maybe, let's say, 10 times, and this set of code would repeat J number of times every single time the I loop ran. So overall, this would happen J into I number of times. However, the fun fact is that when we're coding like this, we have access to the value I and we have access to the value J. So let's say we don't want this J to happen 10 times every single time. Instead of starting J at a value of 0, we could start J at a value of I. So we could initialize J is equal to the value of I and then make sure that J goes from I all the way to 10. So that would mean that when I is equal to something like 9, this for loop would run only once. However, in Blender, we do not have this variable, so we have to manually create that variable so that we can use it. This is very important because remember, this inner lines that we were creating, we actually did not need to create it from 0 every time. Once we were at 1, we did not need to check 1 to 0, then 1 to 1, and then 1 to 2. We directly needed to start from whatever the I value was and then check the next value. So we could start directly from J is equal to I, check for J plus 1. So we could directly start from I or I plus 1. So we have to recreate this in our repeat zones. Let's go ahead and first get out this variable. So how do we know what variable or what number of iteration this is going through? That's very simple to do. We can just search for a math node. We can add in a value of 1 and have some number start at a value of 0, get 1 added every single time this loop repeats. So let's take a new output from here, plug that into the first socket and bring this in over here. Now, in our side panel over here, we can go to our node tab and make sure that you have the input node or the output node selected. And there you'll see you have this new value that you just created. Now we need to name this as maybe some counter variable. So let's call this counter for the outer loop. So we'll call it counter underscore outer. Apart from that, I don't want it to be a floating type value. I want it to be an integer because we're actually going to use these as the indices as well. So that way we get access to the iteration number. Now, how many iterations were there supposed to be? There were supposed to be the same number of iterations as the number of points that we had over here. So let's go ahead and figure out how many points we have. We can do that using something called a domain size node. The domain size gives us the point count for whatever input geometry we give. So we can plug this in over here. But remember, we don't want the point count for a mesh. We want it for a point cloud. So let's change this from mesh to point cloud, and now we have the point count. Remember, while we did the calculations, we saw that we needed the number of points there were minus 1. So let's search for a math node. Let's change this from add to subtract. Let's subtract a value of 1 from this point count and plug that into the number of iterations. So that gives us the entirety for the outer loop. But remember, this is now having an outer going from 0, 1, 2, 3 all the way to whatever the point count is, which in this case is 50. But when we were at point 0, we needed an inner loop that would go to all of the other numbers. So how do we create that? Let's go ahead and duplicate this repeat zone by pressing Shift A and searching for another repeat zone and simply plugging that in over here, just like this. Now we need to figure out the number of iterations this is going to go through. If we're using this outer counter as the indices, if this is at an index value of 0, we want this to go from a value of 1 to 2, 3, so on and so forth. So we can actually subtract this value from the domain size over here to get the correct number of iterations for this inner loop. For example, if we're already on the 49th index, that means there should be only one more connection that we need to make from 49 to 50, because the rest of all of the connections would have already been made. So that's why we need to do 50 minus whatever index count is over here, and that should be the number of times this repeats. So let's press Shift A, search for a math node, change it from add to subtract, and let's subtract this value from this value over here and plug that into the number of iterations right over there. Now, just like how we had to create a counter variable over here, we need to create a counter variable over here. And I'm going to do this in a slightly different way. So here we had the indices going from 0 all the way to the max number of iterations that we created over here. On the other hand, for this, I want the iterations to occur from the largest index down to the smallest index. Hopefully I can explain this properly. In our points, we had indices 0, 1, 2, 3, 4. This outer iteration is going from an index value of 0, then 1, then 2, then 3, and so on and so forth. But this inner loop, since let's assume I'm at an index value of 2, I want the inner loop to check first 4 and then 3. Similarly, if I'm on an index of 1, I'll check 4, then I'll check 3, then I'll check 2. So that's the way it's going to work. It's actually not too hard to do. Instead of an add node, we're going to actually subtract one. So let's press Shift D to duplicate it, switch this from add to subtract, and let's subtract a value of 1 every single time. Let's plug this in just like that, but we have to give it an initial value. So that initial value can simply be the domain size minus 1. So let's plug that in right there, and that's it. That works just as much. On the other hand, it was completely possible to also go from the lowest value to the highest value, and to do that, we'd actually start from counter outer. So we plug that in over here, and instead of subtract, we add. And in this situation, if we were at point 1, we'd first check with 2, then with 3, then with 4. So technically this also works, and since we are figuring out our counter outer variable over here, we might as well use it. It's really up to you. The result is going to be the exact same, should not make a difference, but the aim is to understand exactly why you're doing what you're doing so that you can implement it in your own animations when you need to. For the time being, let's just keep it just like this. And now we have the right number of iterations, but let's go ahead and change this value to call it inner counter. So let's rename this from value to inner counter. And now let's actually do what we are supposed to be doing. What we need is to add in a new line for every single one of these iterations and have that line attached to each of the other points. So how do we add in a new point every single time? So the way we add in a new point every time is by using a join geometry node. Let's search for a join geometry. Let's plug that in right here. And what do we want to join in? We want to join in a curve line. So let's search for a curve line. And for now, let's just plug this into the join geometry. So what we get is the right number of lines, but they're all present in the exact same place at the center. We need to move these to the correct positions. How do we do that? The first thing we need is to actually figure out the position of each and every single one of these points. So that's fairly simple to do. All we do is search for a sample index node. We can plug that in right here, and we can use that value to get the position of whichever index we want. Now this is going to be for the outer indices. So let's see, this outer is going from index 0. So maybe let's say this is index 0. We want to check the outer index. So let's plug that in right here. And what do we want? We want the position of whatever is at index 0. So we have to change this from float to vector because position is a vector. And what value do we want? The position. So let's press Shift A, search for position, and now we can plug that into the vector, and the output of this will be the position of index 0. So for the curve line, I want every single one of the starting points of the curve to go to that particular point. So let's press Shift A, search for a set position node, and the offset is going to be this particular value. However, I don't want this for both the start as well as the end. I want it only for the start. So we have to use this selection. How do we use the selection? We press Shift A and search for an index node. And remember, each curve has 2 points right now, a start and an end. So the indices are going 0, 1, 2, 3, 4, 5, 6, 7. So all the starts are even and all the ends are odd. So we could do that and filter out by using a math node, dividing by 2, or using the modulo function for 2, comparing that, or something that I haven't tried before, we should be able to just search for a curve tip node and we should be getting this tip selection. If we plug this into the selection, I see something is happening, but it's probably not what I want. So what I will do is, instead of using the tip selection, I'm going to use the base. So for that, I have to search for a Boolean math node, plug that in right here and change it from and to not. So now you can see they all go to the exact positions that we wanted them to go to. Now let's go ahead and change all of these tips as well to go to the correct positions. So that is going to be this inner counter that we had. So now for all of these tips, let's go ahead and sample the position of the points at the inner counter. So let's press Shift D to duplicate this. We're checking for the position itself. The geometry is going to be the exact same geometry. However, this time we're going to use the inner counter as the index. Now let's duplicate this set position, plug the value into the offset, and that went crazy. Obviously, we don't want that to move for both the points. We want it to move only for the tips. So let's plug that into the selection. And I don't want this to be an offset. I actually want this to be the position itself. So that is absolutely perfect, exactly the way we wanted it. So just to understand exactly what we're doing, once again, the outer node has this outer counter that's going 0, 1, 2 all the way to the last index -1. Now every time that happens, we have this inner loop as well that's starting from that number and essentially going through all of the remaining numbers as well. Now we're sampling the position at the original point and moving all of the curves to that point, and then we're sampling the position of all of these inner points that are going through the rest of them and then setting the position to all of those points. Hopefully that makes sense. So for the outer loop, we're going from 0, 1, 2, 3 and so on and so forth, and then in the inner loop that's going from the next index all the way to the rest, what we do is we add in one line and then the base of that line is shifted to the position of whatever the outer index is. So let's say for the outer loop of 0, all of the lines that are added in will all be sent to position 0. Then for the other ends of those curves, we find out the position of all of the inner counter indices which are going from the next index onward, and then we set the position for all of those tips to all of those, and that's what creates this particular plexus where we have one line being drawn from every point to every other point. So that works perfectly well. Now we can go ahead and delete lines that are a bit too long so that we don't have this many connections. That's pretty simple to do. All we have to do is search for a delete geometry and then delete anything that is longer than a specific amount. So let's search for a delete geometry node, plug that in right here. And what do we want to delete? We want to delete splines. So we'll change this from point to spline. And what do we want to delete? We want to delete if the spline is larger than a certain amount. So we search for curve info so that we can figure out what the length of each curve is. So now we have to compare the length to something else. So we search for a compare node and we say, is the length greater than, let's say, 1 meter? Then the line should be deleted or else it shouldn't. So now you can see everything that's greater than 1 meter has been deleted and we're left with only these few points. Let's start increasing this and you should get more and more to start appearing. So that is exactly what we want. So now with some value like this, if we were to let the animation play, you should be able to see some new lines being created, like this one was just created, whereas a few frames ago the line was not present because it became too long to fit the condition. So you can see over here the line is deleted, but as we play through the frames they come close enough and the line is created once again. So just like that we get this real plexus effect, which is amazing, and we did all of it using nested loops within Blender, which is just something really cool and I've been waiting to create. Now the rest of this tutorial is just going to be cleaning this up to create something that is renderable, and essentially right now everything is just curves. So if you were to switch off overlays, you can see all of those disappear. And apart from that, there's a few other things as well that we can do, which was actually asked by one of my viewers on my previous Plexus tutorial. They wanted it such that the longer the line is, the thinner the line should be, and the shorter it is, the fatter it should be. So we're going to create that particular effect, but we're not going to go into actually texturing this particular Plexus because the texturing is very much similar to the previous Plexus tutorial as well. So you can definitely watch that if you haven't already. For now, let's go ahead and create this into real geometry where the closer lines are fat and the longer longer lines are thin. So let's press Shift A and search for a curve to mesh node. Now when you plug this curve to mesh node in over here, you're going to get this little warning because the input geometry also has point cloud. So if you actually take a look of this, you see there's two types of geometries. There is a point cloud with 50 points in it, as well as a curve with 518 splines. Essentially, when you do a curve to mesh, only the curve sections are going to be affected. So we don't need to bother about this warning because the point cloud will be ignored. However, if you do want to remove this warning, that's also very simple to do. First up, press Shift A and search for a delete geometry, and we want to delete the points itself, but the selection is going to be if the index is greater than the number of points there are. So we press Shift A, search for an index node, and we're going to search for a compare node, and we're going to compare if the index is lesser than or equal to the actual number of points there are. Only then will it be deleted. So how do we check the number of points? We use a domain size. So let's search for the domain size, plug this geometry into the input geometry, change this from mesh to point cloud, and plug this point count in right over there. Result can go into the selection. So now you see the warning is gone because all of the points have been deleted and we're left with just the curves. Now for the profile curve, we're going to press Shift A and search for a curve circle, and we're going to change this resolution down to something like 5, and radius I'm going to keep something like, let's go with 0.1 for now, but you'll see we'll be changing the radius very soon. So this is what we currently have. Let's go ahead and make it such that the longer ones are thinner. For that, we press Shift A and search for a set curve radius node, and we plug that in right here. Now this radius is going to be dependent on the curve length. So how do we find out the curve length? The same way that we did just over here, where we take this curve info and take the length node. So let's press Shift D to duplicate it and then take this length. And what we're going to do is, if we were to plug this in directly over here, you see the longer ones are going to be fatter and the closer ones are going to be thinner. That's not what we want. We want it to be inverse. So to make something inverted, we're going to search for a math node and simply find the reciprocal by making this as 1 divided by something. So let's change this to divide, make the first value as 1 and the second value as the length. So now you see, if we make it 1 divided by this, the longer ones are going to be thinner and the shorter ones are going to be very, very fat. Let's go ahead and just decrease this radius even more. So let's go with maybe 0.05, and that looks great. However, there are a few that become far too fat if by chance they get too close. In order to fix that, what we can do is we can actually clamp this off. So that way, the fattest it's ever going to be is going to be a value of 1, and it's never going to get fatter than that. On the other hand, it'll keep getting thinner and thinner until it becomes so thin that it gets deleted, and I think that looks perfect. Now that we have these, we need to actually bring in the points, and for that we're going to search for a join geometry node, plug that in right here, and we have the points present all the way over here. So let's press Shift A, search for an instance on points node, plug this geometry in right over here, and for the instance, let's press Shift A and search for maybe an icosphere. Let's increase the subdivisions to something like 4. Let's change the radius down to 0.1 for now. Let's make sure that it's set to shade smooth by searching for a set shade smooth node, plug the mesh in right over there, plug this into the instance, and take this instance and plug that all the way into the join geometry right over here. And now we have the spheres along with the lines, and that's actually all there is to this animation. Of course, to set materials, you can add in one material for all of the lines over here and another material for the points over here. It's really up to you, but I'm not going to get into all of that in this particular tutorial because it's already very, very long. So with that, you should be able to create stunning Plexus style animations. I really hope this video was useful to you and you enjoyed the tutorial and learned quite a bit about the repeat zone and how you can implement it in creating amazing abstract animations. Be sure to not go overboard with this because slight changes here or there might crash Blender because of the looping nature, where it's actually calculating that many loops every single frame. I will be posting videos every single day. However, I might miss 1 or 2 days in between until the new year. Realistically, I'll try to upload about 15 videos until the start of the next year. So until my next video comes out, hopefully tomorrow, thank you so much for watching. Keep creating and don't forget to stay creative.